Hey, how's it going? Welcome to a tutorial video or series, I don't really know which one yet, on how to use the Unreal Engine state tree system to make a pretty simple AI. I know there's a lot of tutorials on the state tree system already, so my thought process for this tutorial, or my goal, I would say, is less of teaching you how to exactly do what I do, but rather to teach you what my thought process is when I'm making an AI system. So I'm approaching this from the perspective of being a programmer that's been signed on to a team, specifically being an AI programmer that's already joining a team that has designers, programmers, artists, whatever, etc., etc. So I'm approaching this whole tutorial and the tips that I give out from that perspective of giving out tips for how to work better in a group and how project organization works and how to make things editable for designers, how to make things available to designers. So that's the whole idea. If you're going to be joining along on the way I have everything set up, I have a pre-episode 1 kind of starting files GitHub thing set up, and you can just go ahead and click this to download it. Just download the zip, extract it, and you'll see a Unreal project in there. Point of notice, I'm using Unreal Engine 5.6.1. I know 5.7 just got released recently. As far as I'm aware, there's not too much of a difference between 5.7 and 5.6.1. Don't quote me on that though. There might be things that are broken, so it's always better to just use the Unreal editor version that I'm using. And yeah, but that should be it. Go ahead and download this, and I'll see you in the project. All right, so this is what our project looks like. As you can see, someone has already come in and set this up, and that someone is me, by the way. Now, one quick thing I do want to point out is because we're using the arena shooter variant, Unreal already has its own AI system set up for the arena shooter NPCs. You can check this out. This is actually really well done. You can take a look at the state tree and try to understand what's happening. They've labeled it really well. And in fact, by the end, I actually might go in and try to give a quick overview on what might be happening, but it's labeled really well by itself, so you should be good to go there. Before we actually start diving into this, it turns out that we actually have a note from our design team that we have to look at. So let's do that real quick. Alrighty, so this is the note we got from our designers. Now, a quick thing that I want to mention is generally when you're working in a team, the designers will have a living document in the form of either a game design document or some sort of just a piece of information on how the game is supposed to be set up. Ideally, in a perfect scenario, the designers, either the narrative designer or the level designer, whoever's working with you as the AI programmer, will come up to you and tell you exactly what they want, either via a memo or just an in-person conversation, whatever it might be. But they'll list out specific details on what they're looking for. This is a very rudimentary version, and usually you don't want to see this as a programmer. But sometimes this is just kind of how it is, especially if your game is in the beginning of the concepting stage. Sometimes you might just get a bit of information about what the designers are kind of looking for, and you just gotta hope and pray that they come up with more details soon. But there is a skill to reading something that's very minimal in what it wants from you and trying to figure out what the designers might actually want in the future. And I'll be doing a little bit of that as well. So let's take a look at our requirements real quick. We have a couple requirements. So the enemy must patrol by picking a point within a radius of its spawn, walking there, and waiting for a bit. Okay? If the enemy sees the player, it needs to chase the player until it reaches a given attack radius. Cool. If the player is within the enemy's attack radius, the enemy will attack, create a random placeholder shoot function for now. Okay? The enemy goes back to patrolling if it loses sight of the player. Okay? Yeah. Cool. Do this or else. So I guess we have to do this now. Let's actually break this down a little bit and see what's exactly going on here. So the enemy must patrol, I'm going to underline that real quick, by picking a point within a radius of its spawn. So it needs to walk there, and it needs to wait for a bit. Okay, interesting. If the enemy sees the player, right, it needs to chase the player until it reaches a given attack radius. Interesting. If the player is within the enemy's attack radius, again, another if statement, the enemy will attack. Okay, create a random placeholder shoot function for now. So I'm assuming when it attacks, it'll go ahead and call this random placeholder shoot function. We weren't told where to create it, so I guess we can kind of decide that on our own. And the enemy goes back to patrolling if it loses sight of the player. Another if statement right here, and a reference to patrolling right here. So based on our analysis, there's a couple things that we can break down. Let me go ahead and create a new page. So a couple quick things we can notice here, right? Number one, we have essentially a few different things we can glean from this document right here. We can notice that there are approximately 3 different distinct behaviors that the enemies will do. One, the enemy will have a patrol behavior, and then it'll have a chase behavior, and then lastly, it'll have an attack behavior. And what we're noticing is that the behaviors and the tasks that the enemy is doing in the attack behavior are very different from the tasks that the enemy is doing in the patrol behavior. For example, during an attack, it doesn't need to pick a point within the radius, it doesn't need to walk there, it doesn't need to wait or anything. During attack, it's just attacking. When you have distinct behaviors that an enemy or anything really takes on, and it does different things in each of those behaviors, that's a perfect case for something that's called the state machine pattern. So the way state machines work is essentially, think of it like this. In this case, we have 3 different behaviors. So we have patrol, chase, attack, and we have different tasks in each one, right? Whenever you have something like this, the way a state machine system basically works is that it identifies 3 different states, and these states allow you to basically encapsulate tasks within a state. So that way you don't have a 5,000 line document of all of the functions an enemy does, and instead you have a reusable state that not only applies to that enemy, but can apply to literally anything. For example, the patrol state can apply to an enemy, but it can also apply to an ally, an NPC, or literally anything at all. So it's always good to encapsulate data in any way you can, and that's exactly what the state machine pattern does. One other thing that it does is that it also establishes transitions between states. So we know patrol goes to chase, chase goes to attack, but here's the important thing. If at any point in both chase and attack, the enemy loses sight of the player, we go straight back to patrol. Another important thing is that if the enemy goes outside of the attack radius that was mentioned here, the enemy needs to chase the player again. So attack can actually go back to chase. So here we have basically a state machine. We have states and the transitions between states. And that's pretty much what the state tree system is. Now, a key distinction I want to mention is that this is just a normal, traditional state machine, whereas the state tree system is a little bit different. It's a hierarchical state machine. So you can have a state that has child states within it. For example, we can have 2 different kinds of states. We can have a no player parent state, and we can also have a player found parent state. So by themselves, these 2 will not be doing much. The only distinction is that whenever we find the player, we go from no player to player found, and whenever we lose the player, we go from player found to no player. Right now, the way we have this set up is that no player could technically have child states. This could have a child state called patrol. So whenever we're actually in the no player state, we'll actually be running all the logic in the patrol state as well. And then player found has 2 states called chase and has a state called attack. This is an important distinction to make between a traditional state machine and Unreal's state tree system, because they work a little bit different, and you can do very similar things in either, but you'll notice that the transitions in the state tree system are a lot more organized. In a traditional state machine, you have transitions going from one state to another, and literally almost every state is hooked up, right? Whereas for a state tree, not only is the transition between no player and player found very simple and only managed between 2 states, but the actual interior states don't even have to refer to each other aside from chase, which needs to go to attack. So there's very little transitioning happening, which makes everything a lot easier to understand. An important thing that I don't know if I fully mentioned yet, but whenever we're in a child state, like let's say for example right now we're in the patrol, right? Everything in the no player state or its parent state is still running. So all of the tasks are still running, all the transitions are still running, everything is still running in a parent state whenever we're in the child state. It's important to keep track of that, and we'll actually take a look at what that's going to look like as we're actually making the AI. Hey, Editing Sai here. This is the end of episode 1, or episode 0, I should say. It's a bit more of a setup episode, but in the next episode, we'll actually be covering how to make the different states. We'll start with the patrol state, and we'll see if we can make the attack state and the chase state as well. So yeah, I'll see you in the next episode.